Okay, so we talked about our two favorite quantum instructions on one qubit, which are toggle and Hadamard. But actually, we can make some more instructions on one qubit by writing little quantum programs. So let's do that. It's 1 in 4 chance. So great. It happened. I'm so happy. Let's do a little subroutine called new operation on A. And it's a little program. 1, we'll do Hadamard on A. And then 2, we'll do toggle A. OK. So what does this do? This transform. We now know that this is a linear transformation on vectors. We can think of it this way. So some kind of linear transformation. What is that linear transformation? Well, we know this one is a reflection, and then we know this one is another reflection. So actually, before we do this specific one, let's more generally, let's go straight to the general case. Let's talk about the nature of the composition of two reflections. I don't know. This is like a geometry topic. Maybe you never thought about this geometry topic before. Let's see. So let's say, actually, there's no real reason to have this circle in the picture, but let's say you have two reflections. Let's say this is axis 1 for your first reflection. And let's say axis 2 is at 40 degrees to it. How much is 40 degrees? Maybe like this. So this is axis 2. And let's say this angle and this angle are 40 degrees. Okay? And I want to think about like the action of first reflecting through this mirror and then reflecting through that mirror. Okay? So let's see what happens when we do that. So let's pick a generic vector to start at. So here's my generic vector to start at, this one. And let's say that this is 10 degrees. Again, I just picked 10 sort of random. So yeah, where does this blue vector go? So we do the first reflection across this axis, and it goes here. So this is also 10 degrees, of course. And so then this amount, by the way, is therefore 30 degrees. This is 40 minus 10. And now we do the second reflection through this green axis, and now the vector is like 30 degrees away from the green axis, so it goes like 30 degrees away. This is a poorly drawn diagram, but it goes 30 degrees away this way, here. So how far did the vector eventually travel? It went from here, that was 20 degrees, and then it went here, which was 60 degrees. So like overall, it went 80 degrees. Now, if you look at this diagram, it like went more than 80 degrees because I drew wrong. But I hope you agree that the math is right. I guess probably this 10 degrees should have been like way narrower in the picture. Okay, so it seems that like doing the composition of these two reflections rotated the vector. And how much did it rotate it? It rotated by 80 degrees, which happens to be double 40 degrees. And this is not a coincidence. This is what happens in general when you do two reflections. Two reflections equals a rotation. That's a general life fact. So in general, it's sort of like a proof by picture. The composition, if two reflection axes are at angle theta, the most popular name for an angle, then the composite operation is rotation by 2 theta. Okay, you do have to pay attention to like clockwise or counterclockwise. Like when I say the angle between them is theta, I mean when you go from axis 1 to axis 2. And the rotation is like in that same clockwise or counterclockwise direction. And why is that true? Well, I mean, I'll just repeat the same picture, but with letters. I'll just say because if the vector starts at angle alpha was 10 degrees here, from axis 1, like the first reflection rotates it 2 alpha. And then, like, now it's at angle theta minus alpha. Like, these used to be theta, but now we got some alpha off here. And the second rotates it 2 theta minus alpha. And then if you add these up, that's 2 theta. Okay? Somehow, like, I don't have, like, the world's, like, most clear intuitive picture. Like, if you just, like, asked me, like, woke me up at 4 a.m. and said, like, if you do 2 reflections, like, why is it a rotation? I'd be like, I don't know. But it is. So maybe you guys see a way. So, okay. So actually, therefore, we should know what is the nature of this composite operation. Can somebody tell me? It is a rotation, but I don't think it's 22.5 degrees. Yeah? I think it's 45 degrees, because like Hadamard is reflection through this 22.5 degree axis, and like toggle is rotation through this like 45 degree axis. So the angle between the two axes is 45 minus 22.5 is 22.5. So the rotation is double that, which is 45. So this is rotation by 45 degrees, aka 1/8 of a turn, and then counterclockwise if you want to be precise. Okay. And we can kind of check that, right? Like, if we do this new operation, let's see if I can go on tiptoes. If we do it on 0, well, then Hadamard takes 0 to plus, and toggle, plus is this one, toggle doesn't change plus, so it goes to plus. On the other hand, if we do Hadamard to 1, that goes to ket minus, which is this one. And then if we do toggle, it goes to negative ket minus. Okay, so at least overall, we know that ket 0 went to plus. That's rotation by 45 degrees. And ket 1 went to negative minus. That's also rotation by 45 degrees. So it checks out. Good. And what's funny is, like, okay, from this you know that if I were to do new op 8 times in a row, then whatever vector came in would get rotated 1/8 of a turn 8 times, and it would come all the way back around to itself. So doing the 16 lines of code that consist of new op repeated 8 times, that's equivalent to doing nothing. Which is kind of funny. I mean, like, if you had to prove that straight off without geometry, it might be a little bit annoying. Okay. Technically, there were like 2 other 1-qubit operations. Technically, there are 2 other 1-qubit operations that I like granted to you, and I gave you these very suggestive names, clockwise and counterclockwise. These were maybe not like the most correct terms, as we're going to see, but let's look at them again now. So I had this like clockwise operation, which I basically defined by its matrix, 0.8 minus 0.6, 0.6, 0.8. Remember, this is 0, 1, 0, 1. It goes like this. And counterclockwise looked kind of similar, except it was, well, the transpose of this. 0.8 minus 0.6, 0.6, 0.8. And maybe a better name for these would not have been clockwise, but maybe rotation by about negative 36.87 degrees, which is about 0.1024 turns, or taus. And counterclockwise is basically the same thing, only it's rotation by about positive 36.87 degrees, or about, oops, that's negative, positive point, just over 1/10 of a turn. Mathematicians have this like funny convention that to them like a positive angle means counterclockwise, and a negative angle means clockwise. So we just, I don't know, we're going to go with that. Yeah, so why do these paths diagrams, if you will, correspond to actual rotations? Well, you may have seen before in your life that these are rotation matrices, but let's try to plot it. So what does, like, for example, clockwise say? Clockwise says that if you start out at 0, which this is 0, ket 0, then what you get to is 0.8 on ket 0 and minus 0.6 on ket 1. So you get this column vector, 0.8 minus 0.6. So it's like 0.8 minus 0.6. Okay, so this one goes to this one. And moreover, this instruction called clockwise, if you start at ket 1, 1 comma 0, or 0 comma 1, you go to 0.6 on 0 and 0.8 on 1, which is like 0.6 over here and 0.8. Again, it's not the greatest diagram, but this is 0.6, 0.8. Okay, and it turns out these two angles are the same. And the actual numerical value is, I don't know, arctan of 0.8 over 0.6 or something, which is about 36 degrees, 37 degrees. Okay. And again, like this actually only shows that, well, it shows that like ket 0 gets rotated by like 37 degrees, and like ket 1 gets rotated by about 37 degrees. How do we actually know that like every vector gets rotated by 37 degrees when you plug it into this paths diagram or matrix? I somehow still try to like think of the same picture, remembering that like clockwise is a linear transformation. So if I have like, let's say this vector, which is like basically the red vector, except I've nudged it upwards by a little bit of this green vector, then where does this black vector go? It basically goes to here, except I also have to apply clockwise to this little nudge, and this little nudge also rotates it by 37 degrees. So like, here I also rotate by like another 37 degrees. And yeah, that makes sense. And so then like the new vector is this one. So somehow like that's how I try to see why this black vector goes to this black vector. So indeed, like this rotates every vector by 37 degrees. Okay. Good. So I guess in principle, like at the beginning of the course, I was like, okay, here are all the 1-qubit pseudocode instructions I'm going to allow you. I'm going to give you toggle. I'm going to give you Hadamard. I'll also give you like, these two weird clockwise and counterclockwise just because it was nice to get some amplitudes that weren't square root of a halves. They had like other short names like 0.8 and 0.6. And we see that you can like build up new 1-qubit operations by combining them. Like we combined these two, and we got like rotation by an eighth of a turn. But actually, if you just put these together, like you'll only get like reflections, or you'll only get like rotations by multiples of 1/8 of a turn. But actually, with these, I mean, there's sort of a homework problem about this. With this, once you have this like clockwise or counterclockwise thing, somehow because this is not like a rational amount, you can get all sorts of rotations by doing this repeatedly. So, yeah, what I'm about to tell you is like not super critical, but like I kind of think of it as fun. Let's consider this code. I don't know, new up. On A, we'll just do repeat 10 times. I don't know, counterclockwise on A. Now I'll ask, okay, this is some code I can do to 1 qubit. What does it do? Well, we just saw that counterclockwise, if you do it, it rotates every vector by a little bit more than 1/10 of a turn around the circle. So if we do it 10 times, it'll be like a little bit more than one way around the circle. Okay, so this thing is like a rotation by 10 times this. So like about 1.024 turns around the circle, or taus. But of course, actually, that's a funny way to put it, right? Because if you go like all the way around the circle and then you go like a little bit more, that's the same as just rotating by 0.024 turns. So this instruction is also like equivalent to by 0.024 turns around the circle. So like about a quarter of a tenth, like about 1/40th of the way around the circle. Okay, if you crunch the numbers, this is like, I don't know, 0.048 radians, pi radians is like 8.7 degrees. Okay, so that's kind of funny. Like, just using this instruction, we can get like a new composite instruction that rotates by like a little bit, 8.7 degrees, by doing this like 10 times. Sort of funny. And yeah, this is about 1/40th of a way around the circle. Like, if you now repeat this 41 times, in other words, you do like the counterclockwise operation 410 times in a row, then it's 41 times this. It's rotation by about 41 times 0.024 turns, which, according to my computer, is 0.99 turns. So you go like 99% of the way around the circle, which is also equivalent to going like clockwise. I mean, this is negative 0.01 turns, or it's going like clockwise about 1% away around the circle. So this is like equivalent to like clockwise by about, what is 1% of 360? I guess is about 3.6. So by about 3.6 degrees. So it's kind of funny, like, you know, just by having this like one counterclockwise instruction, if we repeat it 410 times in a row, it's equivalent to doing clockwise by like 3.6 degrees. And actually, if you keep goofing around by it like this, like you can make like rotations by like any little amount you want by repeating these as many times as you want. But let me not be annoying like that to you. Let me just like hereby declare I'm now granting you some more 1-qubit operations. I grant you rotation by any angle you want. Okay, so in our new quantum pseudocode instructions are you can have any rotation operation by any angle you want. And you know, if you really wanted, you could like build these up by like enough copies of these rotations, but I won't make you do this. So hereby granted the instruction, you know, rotation by some theta, you know, positive or negative on A for any angle theta. Okay, and this will make our lives very pleasant to have this operation. And actually, why can I allow this to you? Well, remember, what are the truly allowed by physics operations? The truly allowed operations in physics are the linear transformations which are unitary, the linear transformations which don't change the lengths of vectors. And, you know, rotation, it sounds a bit funny, but rotation is a linear transformation. If you have the sum of two vectors and you rotate both of them, you get the rotation of the sum vector. And it's unitary, because of course if you rotate a vector, it doesn't change its length. So like we know by the laws of physics that like this is physically possible always, and so now I'm just going to say, yes, I give you a pseudocode instruction that corresponds to that. Okay, so we've now seen on these 1-qubit operations, we've seen some rotations and we've seen some reflections. And these are unitary, length-preserving linear transformations. You might ask, are there any other linear transformations that are not rotations or reflections? Like, it's a bit of a head-scratcher. Are there any linear transformations that preserve lengths other than rotations and reflections? And the answer, which we'll talk about next time, which is in 1 week, is no. Even in higher dimensions, any real unitary linear transformation, real means we only ever talk about real amplitudes, which is what we're doing in this course, is a rotation/reflection. And this is true not only in n dimensions, but in any number of dimensions. So we know if you have like a 3-qubit state, that's like an 8-dimensional vector, and like a 3-qubit operation is a linear transformation in 8 dimensions, but it's a unitary one. So any 3-qubit operation, even if A and B then toggle C, that instruction is really a rotation in 8 dimensions. So in fact, every quantum computer program is just doing a bunch of rotations and reflections to some vectors. So that's how we're going to think about it for a lot of the rest of the course, like the geometric rotational nature of quantum algorithms. OK, so I'll see you at my office hours today, 12:45. And then I'll see you later. In fact, I'm out of town during the test. So I'll see you really next Thursday. Bye.